is in person on paper. Final is in person on paper. And test 3 is online to take home, but it has less weight, right? I think it's 10%. Each test, otherwise, in person on paper is 20. Okay, and then pop quizzes, I'm going to try to give you more points, like credits, like bonuses. Now, for the final, don't miss the final because I have to go back to Europe just after the final. So don't, have a flat tire or whatever I saw as excuses. So for final, don't miss the final, okay? Otherwise, I will have you come at 7 a.m. the day after. Otherwise, you have a 0. So don't miss the final. Just saying. So anyway, we have to keep moving. Make sure you do your assignments properly. Like, don't look at the solutions. I know you can always find the solutions, but make sure you work them out seriously. And then for the second trial, you can pick somewhere. For the first trial, you have to do them seriously. You have to use your brain for plasticity. There is something called brain plasticity. It's a good exercise. You can use your textbook or slides. And as I've said, you're going to pass the class. Most of you, like 99%, will pass the class. But it's not about passing the class. It's building up the skills, right? So anyway, let's move on. So last time we talked about electric field a lot. And now we also talked about potential. So what is electric potential? That will be the potential energy, the potential energy per unit charge. So for 1 coulomb. Okay. So when you say you have 120 volt, I show you that 120 volt from the outlet, that will mean that the hot wire, okay, will bring each coulomb of charge at a potential energy of 120 joule relative to the ground. Because electricity we get from the grid, okay, the return path is the ground. So that's why it could be so dangerous, because if you touch something and there is a leak somewhere, right, it will go through you, because you will be the least resistance path to go back to the ground. Okay, so voltage is a property of 2 points. Voltage is a property of 2 points, and it's going to be potential energy per 1 coulomb. So let's go back to this very simple distribution. So that's going to be a point charge, okay? It's ideal. Usually you have a Van Graaff generator, for example, not like a single point, but let's say you have a single point. We already know what's the electric field. So if you go back here just to review, the electric field of a point charge, of a single charge, you have it here. Okay, so electric field will be the force acting on the 1 coulomb charge placed at some location in space. Okay, so anyway, so let's go back to that one positive charge. Where is it? One positive charge, and then we're going to talk about equipotential. So you have to think of potential, right, or voltage as altitude. So for example, if you take a mass here in my hand relative to the ground, if I increase the altitude, okay, I'm going to increase the potential energy. And if I have 1 kilogram mass, so that will be 1 unit of mass, I can increase the potential energy of that 1 kilogram relative to the ground. So we're going to say the same thing for voltage, right? Voltage will be potential energy per unit charge. So it's like altitude, right? So let me show you how it works, and then you will understand better. We have these amazing simulations. When I was in school long time ago, we didn't have internet, we didn't have any of those, so we really had to use the textbook. So what you see here, what is that? The electric field outgoing. So that could be a proton. In that case, is 1 nanocoulomb of charge, right? And then I'm going to use this here. I'm going to trace what we call equipotential, and I will explain what it means, right? So I can move further. So here you have 19.7 volt. Here it could be infinity because it's a point charge, so very, very strong potential. As I go inside, goes to infinity, and then it's going to decrease, and then it's going to decrease, and then very, very far away, which is infinity, so far away, will be the ground, and that's going to be, it's going to go at 0, right? So far away, it's going to go to 0. So there is an asymptote over there. Okay, so what's the meaning? So first of all, can you notice the electric field, the direction of the electric field relative to those equipotential? The direction, are they parallel, random angle, or they are perpendicular? Perpendicular, very good, right? So it's showing you, okay, the largest slope going downhill. So this here you have visualized, you have to visualize it like some kind of hill here, right? And the electric field will show you the direction of the largest slope. So if you have water, going downstream, it will follow the slope, the largest slope, the steepest slope. Does it make sense? Okay, so what's the meaning of the voltage? If you take a 1 coulomb of charge, so this is my 1 coulomb of charge here, right? Take my sensor. So here, very far away, it's not going to feel anything. So it's at infinity. What's going to happen if I bring it? So this is positive. So positive will repel. So I have to do work. Okay, let me see if I can push it. Yeah, but the work is so hard. So hard. Sure. Okay, so the work that I had to do on that positive charge, and then I have to pin it, okay? Otherwise, it wants to go and have some acceleration. So the work I have to do to bring that charge from very far away to that position here, that's going to be 19.7 joule per coulomb. So if you have 3 coulomb, that will mean 3 times the work that you have to do. So what you are doing here, you are transferring energy from you to the system. So your work turns into potential energy. You have to do work against the electric field. And if you go back again to your equation sheet here, you see we are doing there. You see that, where is it? Potential energy here. You see the voltage is just the potential energy per unit charge. And again, as defined before, the voltage, okay, so it's the electric potential difference, is the work that has to be done against the electric field. The goal in life of the electric field is to lower the potential energy. Likewise, if you have a mass here, the job of gravity, so you can imagine you have an invisible spring being stretched out and very upset. So gravity wants to bring it down to a lower level of energy. Okay, so to have a voltage, a property of 2 points, you have to do work against the electric field. Yes. But if you let go, what's going to happen? It's going to go downhill. So all that potential energy is going to turn into kinetic energy. It's just that in that simulation, I have to glue it. Okay, there is some kind of glue, but in reality, if I let go, zero, it's going to go into kinetic energy, right? So what does it say doing work. Okay, there is no inside the battery or power supply. You don't have some kind of leprochon, right? Taking a charge and pushing it. So inside the battery, you have some chemical reaction that will be exothermic and that will bring the charge 1 coulomb to a higher level of energy. Okay, it's chemistry. Actually, it's more like physics, right? It's like when you are making ATP in the body, it's just transfer of energy. And I don't know, when muscles contract, is using ATP to increase the potential energy of calcium, and then calcium use that energy to change the shape of proteins, and that make your muscle contract, right?
Myosin attachment, the actin
Yeah.
allows it to contract, and then to stick them together, they have to be
Folded again.
yeah.
So when you unfold them, they have high potential energy, and then it goes to mechanical energy, right? I understand. I don't know the terms, but you know, yes. What is it called?
Myosin and actin, the proteins.
Okay, that's right. Yes.
Which chapter is this in the textbook?
It's 21 or 22. I'm maybe 23. I'm gonna get to that because I have a textbook reference. Maybe 23. So it's called potential. Okay. So this called equipotential. So if you take this charge, okay, and this charge, let's say, is 1 coulomb. So I take that charge and I push it here, right? The energy that you have to do against the electric field, or that a chemical reaction in the human body has to do against the electric field, because in the body everything is electrical. It's all about distribution of charges, it's all about electrostatics. So that energy that you have to provide against electric field will be 8.2 minus 5.4. So voltage is the potential energy per 1 coulomb relative to, so in that case will be relative to the ground. Is that clear? So what it will look like, okay, so if you want to plot potential energy versus distance, it will look like a hill, right? So if I say I want to plot here, that will be the distance, and I have a positive charge here. So that will be potential energy. Okay, so if I want to plot, to make a graph, so here it's going to be, if it's a point charge, it's going to be infinite, but it will be something like this. Go here, go up, and then it's going to go down. So that will be for a point charge. Okay, so the potential energy, okay, in the vicinity of a point charge will be K, the charge Q, this is Q, and that will be the distance R. So as I move away, you see it should be infinity here. You see this is 1 over R, the distance from the point charge. Is that surprising? No, it's not, because if you remember the electric field, it was K Q R squared. And how do you go to one? What do you take? The integral? Yeah, you take the integral. And if you go here, you have to take the derivative. So that means we're going to see that the electric field is the derivative of the potential. Okay? And the potential is the integral. We already seen that. Okay, so they are reciprocal for each other. So in chemistry, you use that a lot because it means that the electric field or any conservative force derived from a potential. Okay, just touching on calculus. Okay, so next, what's going to happen? What do you think is going to happen now if I have a negative charge? So positive charge I have a hill, right? I have a hill like this. What do you think? Good morning. What's going to happen if I have a negative charge? Very good. I'm going to have a valley, right? I'm going to have a dip. So if I have a negative charge, right, here, you see the electric field wants to go inward, so it's converging. Okay, you can describe that in math using in math, no, you use convergent, the operator called divergent, because it's converging. Electrostatics, electric field is always converging or diverging in electrostatic. So what do you have now? You have a dip, okay? And the potential is going to be negative, okay? Because now I have to hold the charge here. The charge wants to go in this direction. With a positive charge, it was repelled. Now it's going to be attracted. So it really wants to go, right? So I have to hold it. Don't go. Don't be impatient, right? So I have to hold it because it really wants to go. So it wants to go down. So it's like water falling. It wants to go downhill, right? But again, it's going to have negative potential energy. And if I let go, boom, it wants to go there. If I let go, all that potential energy is going to turn into kinetic energy. Okay, so if I try to represent that, it's going to be something like this. That will be a negative charge, and it makes sense that if you put a positive charge there, it will go down. Is that clear? You get a feeling? Then you have to think of gravity, right? So what will be the potential for a point charge? If it's negative, the potential will be negative. If it's positive, the potential will be positive. Okay, so it's a scalar quantity, which means it's not a vector. So it's much easier to deal with. Because when you're going to use a superposition principle, you just add. But electric field, as you saw for the test, you need to do the x component, the y component, and the angle. Yes. Yeah, very good. Very good. Excellent question. Exactly. So I'm going to build on your question, which is a very good question. And I know his name, by the way. So you ask me who I know and who I don't know. I know his name. From last semester, but for some reason now you sit over there. I don't know why. But let's say you have a dipole, very, very important in chemistry. Okay, you have induced dipole and you have permanent dipole. Same thing, very important in cardiology. Cardiology, the heart will behave like a dipole as well. So this is a dipole. And now if I make interesting equipotential here, so close to the minus, it's going to win. So you go down. Okay, you have a throw. But close to the plus, it's going to go up. Okay, you have a heel. But just in the middle, what is it that you're going to have? If you have a heel and the up, in the middle, you're going to have a flat. It's going to be flat, right? Then, and I can show you that. Let's say 1.5 should be exactly in the middle, 0.1. So here, the potential is going to be 0. Potential is 0, so no energy. Okay, so this is called a dipole. Very, very important in cardiology. So a dipole, since you ask, will look like this is a dipole. And you see here, there is no potential. Potential is 0. So if you have, for example, you can think of that as, so you have 180 volt, and here you have minus 180 volt, so close to here. So what will be the potential energy between them? I have the computation wrong. Between 180 and minus 180, what do you have? No. Between 180 and 0. Okay. So you between here and there you have 180. Okay. So imagine you are hiking 180 meters or kilometers, or no, not kilometers, meter, boom, 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 0, and then you go down to minus 180. So what's the difference? Yeah, it's gonna be two 260, 360. Thank you. I don't know why I say 250. 360. It will be 360 volt. Does that make sense? Between 10 meters above and minus 10 meter below, it's going to be 20, right? So the voltage, because remember, voltage is a property of 2 points. So 180 is relative to the ground. Minus 180 is relative to the ground. But 180 and minus 180, between them, you're going to have a potential of 360. So if you place 1 coulomb of charge here, it will have 360 joule relative here. So it's going to go down slope like water, right? So why is it important? For example, you take your outlet, some outlets like for the washing machine, they have 2 hot wires, right? 2 hot wires. You have 120 minus 120 because they are out of phase. If you take electronics, you learn about phase, right? Out of phase. So 120 minus 120, what's going to be the voltage difference or the electric potential difference or the voltage? 120 minus 120 is going to be 240. Why? Because those washing machine and dryer and probably the microwave, they are very, very demanding in energy. And because you don't want to increase the current too much, otherwise the circuit breaker not going to be happy, so you increase the voltage, right? So it's something you're going to use, even if you're not in physics major, doesn't matter. Even if you're an engineer, you have to understand that, hot wires, right? It's really the basic. So anyway, that was a good question. Okay. Now, if you have a capacitor, okay, remember capacitor electric field goes from plus to minus. Now the voltage will decrease at a constant rate. Okay? Because remember we did that already, but for a capacitor you have so the voltage here, voltage, the voltage between those 2 points here will be the electric field times the distance. Okay? So the electric field is constant, is uniform. Do you remember that? So the rate at which the voltage is going down. Okay, so if instead I put an X here, we already talked about that. At that point here, it will be 100 volt. Here it will be 0. So delta V over delta X, that's going to be the electric field. Okay, the electric field, you take the derivative, it's the slope, and it's a constant slope. So your voltage, okay, so the voltage as a function of distance, it's going to decrease at a constant rate. Okay, you're going to have a line. And the slope here, the slope will be the electric field. If you have a point charge in space, you see the voltage, if you do voltage versus the distance, it's going to do something like this. Okay, so in that case, the voltage is kq over the distance, so it's 1 over x. But between the plates of a capacitor, the voltage will decrease at a constant rate. Conclusion, the electric field is the slope of the voltage. Okay? So here, instead of having like a hill here, you're going to have something, a slope. Okay? Now you have to think of equipotentials like contour lines. Like if you go hiking It's very hard to have something in 3D. If you have an app with a GPS, they will show you the contour line. Okay, so it works the same. Voltage is like height. The electric field will be the slope, showing you the slope, the largest slope. Okay, where it's going down the fastest. So what about a Van Graaff generator? Okay, so I'm going to show you the map, but just to understand what's going on here, you have a Van Graaff generator. Is she isolated from the ground? Answer is yes. If Van Graaff generator have very high voltage, but it cannot kill you because it cannot build up enough charges, right? So when you try to put too much charges, it's gonna discharge. It's gonna have a spark. So it won't kill you because it's not so much the voltage that is the issue, is the current. Because current will go for your heart. Heart is an electrical system, so it will contract. So it's not so much a voltage. So that thing can be at 10,000 volts, and she will be okay, and she will be also at 10,000 volts. So when two conductors touch each other, they will be at the same potential. Okay, so that's, and I will show you the math, but they will be at the same potential. So she will be at 10,000 volts relative to the ground. Isn't that amazing? Right? So even though the charges will flow on the outside of her body, so that's why here the hair repel each other, but they cannot find a path to the ground. So she's not going to feel anything. Okay? Only if she touches someone, then of course she will feel shock, but she won't die. Okay, so equipotential inside, remember the electric field is inside conductors, the electric field is always zero. But the potential is not zero. It will be the same as the outside. So if this is 10,000 inside, it's going to be 10,000. That's going to be 10,000 inside, it's going to be 10,000. So I just want to show you the math.
Perfect.
Bless you. I will show you the math. Why? So let's say you have a Van Graaff generator. So that way you learn how to use math, right? How to do a little bit of math. Okay, so what's the definition of the voltage? The voltage, right, is a property of 2 points. So it's an electric potential difference. And it's going to be the work, that's the definition of work, that you have to do against the electric field, because the electric field always wants to bring the system to a lower potential energy. So let's say you go from point A, and let's say point A here, the potential is 10,000 volts, right? Just like this. And you're going to move here to point B, which is inside. Okay? So I'm going to use that equation. I'm going to say the voltage, right, between A and B. So that will be B minus VA, for example, right? So I go from A to B, and I'm going to take 1 coulomb of charge, and I want to know what's going to be the work done from A to B. So what do you think it's going to be here? What's the electric field inside when I go for a walk? It's going to be 0. So that's going to be 0 because you're going to have minus 0 ds, right? So it's going to be 0. So the voltage, the electric potential difference, or the voltage between A and B, it's going to be 0. So the voltage at A will be equals to the voltage at B. So all the conductors will be at the same potential. Okay, so inside is going to be also 10,000 volts. Okay, because the electric field inside equals 0. That's what we call an equipotential. Is that clear? Okay. So now if you want to make a drawing of the Van Graaff generator, inside, so R, okay, so from inside to here, you have an equipotential, 10,000 volts. And as you move away, okay, it's going to be 1 over R. You see, 1 over R, okay? Is that clear? So if I go back to my thing here, if I just take one charge here, let's say it's a Van Graaff generator. I don't know how much, let's say, if it's a point charge, it's going to be infinity, but that does not exist. Let's say I have a very high potential, 1,000 volts, and then the voltage will decrease as 1 over R. 1 over R, and the electric field is always perpendicular to the contour lines. You have to look at them as contour lines. Now let me ask you something. Here I have to do work, right? Do I do work here? Do I do work? No work. Okay, because the force is always perpendicular to the displacement. So if you go along a contour line in a high K, okay, you are not going to do work against gravity. You will be at the same altitude. So it's not going to be too tiring. Okay, of course, if you go uphill, then you have to do work against gravity, and that's going to be hard. And if you go downhill, you want to make sure not to roll down the hill hiking. Okay, you have to do something like this, so otherwise gravity is going to take you downhill. Is that clear? So if you go along the equipotential here, you can go at a constant speed. If you go at a constant speed, there is no work done. Okay, so that's why if something is in orbit along a circular orbit, right, circular trajectory, the centripetal force is always perpendicular to the trajectory, so it's going to move at a constant speed. You are not changing the kinetic energy because there is no work done. If it's an ellipse, right, it's another story. Any question? Okay, so now if that's the same thing that I have done. If you have some kind of conductor, inside the electric field is 0, and outside, if it's a point charge or behaving like a point charge, is going to go as 1 over R squared. The potential is constant inside a conductor, and it will go as 1 over R. Yes. So R here is the size of your Van Graaff generator, right? So if you go here, that will be the size. Okay, so as long as you are between 0 and R, the potential will be the same. And then you are at a distance larger than capital R, then it's going to go down. So here this is the center of your conductor or Van Graaff generator. You are here, right? So when you move from here to there, the potential will be the same. It's called equipotential energy, equipotential. And as you leave, it's going to go down as 1 over R, right? So the variable is lowercase r, and the constant is the radius, the size. So it's a constant. Any question? Yes.
I get where the voltage is constant, but how would there even be any voltage if it's like your fan?
Because voltage is by definition the work done. So once you are here, there won't be any work done because you are doing work only if there is work done, only if there is electric field fighting you. So if there is no electric field fighting you, you are not doing work, which means you are not transferring energy to the charge, which means its potential energy will not increase. Okay? So if I'm doing a hike, and I stay at the same altitude, which is easy in Florida, right? So you are not doing work against gravity. But if you go uphill, you are doing work against gravity, so your potential energy will increase and you won't have the same altitude, like not having the same voltage.
So there, like my question is, like, there is a magnitude to the voltage, it just doesn't change.
Yes.
But because it's like you're already at height, you're just gonna.
Yes. Okay. Because the only thing that can change your voltage is if there is an electric field and you are going along a displacement parallel to it, right? Okay, so that will be the definition. Again, calculus here. And you're going to see for those who are doing electricity, for example, that will be called Kirchhoff law. Okay, so if there is no inductor involved, right, that will be called Kirchhoff law. The consequence of that will be that if you go around the circuit, you're going to add all the voltages, right? For those who already took electricity, not to worry about it. Okay, let's do a problem here. What's going to be the potential here? So you have a positive charge, so that will be the source. It's like wind blowing. There is a source of electric field that is fighting you. If you dare bring a positive charge here close to it, it's going to fight you. So it's like a wind blowing. So you take a 1 coulomb of charge, you're going to bring it from infinity to that distance here. What's going to be the potential here? Okay, so you just have to use the equation. You can show it, right? You can derive it, but because you are all super good, you're all gonna open your textbook and study. So I'm not going to show you the equation, but for a point source here, you have the equation here for a point source. The voltage for a point source is this, okay, because it's the integral of 1 over r squared. So that will be the voltage for a point source. So how much energy you have to use or how much work you have to do to bring 1 coulomb of charge from very far away, so from the ground, close to here. So we are increasing its altitude. So it's just plugging in. Yeah.
Is it a coincidence that me describe voltage as like a what is it kind of like that vector that goes downwards, kind of like as we would have that make it coincidence?
No. It's called a potential well. No. It's the same idea. So if you have an electron and the electron is bound to its nucleus, it will be in a potential well. So it means it's down the well. And if you want to make it break free, you have to give it energy so it can go up the hill. Right. But you're right. In quantum physics, you have little well like this, and yes. So it's the same idea. Very good. Yes. So potential energy is binding. Okay, something you have to do work against to break free.
About 300 volts.
Yeah.
Okay.
So the voltage will be K Q over the distance. So the voltage, so here it's relative to infinity. Okay, so at infinity I say it's actually the ground, potential here is 0. So relative to infinity, that will be 9 times 10 to the 9. The source, 4 times 10 to the negative 8. And the distance here, 1.2. So you don't square. Right? The voltage is the integral of the electric field. And indeed, you're going to get 300 volts. Okay? If instead you have a negative charge, so now the potential makes a valley, a dip. Okay? A well, if you want, it's going to go down. Yes. It's probably we're going to find the electric field, right? No, no, no. We are finding the potential. Okay. If you find the electric field, okay, the electric field will go outward. So the electric field is the same thing, but there is a square. Okay? The electric field is not the same thing. The electric field is a vector. It's like a wave. How do you go from here? How to derive from the voltage, the electric field, you take the derivative. So the electric field will be the derivative of the voltage. Okay, so the electric field derives from potential energy. So any potential energy has a force that tries to lower the potential energy. So it's a derivative. So if I have a negative charge, the voltage can be negative. So negative charge, it will be. So it's going to be the same thing. Negative, oh yeah, so 1.2. So it's going to be minus 300 volt. So if you have a negative charge, that will be at minus 300. If you have a positive charge, that will be at 300. Okay? What is that? Volt. What is the meaning? The meaning will be joule per coulomb, right? So if you place 1 coulomb of charge, it will have an energy of 300 joule. It wants to go this way. If you have 1 coulomb of charge here, it still have potential energy, but it wants to go that way. Okay? So it's minus 300 joule relative to infinity. So what does that mean? When you have a negative potential energy, it means it's trapped. It means it's in jail. It means it's bound. Okay? So if you have molecules, for example, you learn that potential energy will be negative if they are bound together. Okay? That means if you want to break, you need to give energy. Okay? So this is the idea of energy level. Endothermic, yes, takes energy, so lower, you're right. So a positive charge here, placed here, okay, wants to go down. Okay, if you have a negative charge here, a positive charge here will go down. Is that clear? So minus 300 means we are somewhere over there. This is 0, this is minus 300. Is that clear? So you have a negative charge here, and here you have negative 300. So it means if you want to rescue that positive charge, you need to go and push it outside. Okay? Okay? 300 minus 300. Yes.
You could probably you know how you say there's 300 volts would be 300 joules per coulomb. You could probably, because charge is quantized, we could probably find how many joules are the per electron.
Yes, yeah. So if I have, so let's build on this problem here. Okay. So if I have 1 coulomb, so 1 coulomb of charge here, okay, its potential energy, which is the voltage, will be 300 joule per coulomb. Okay, so per coulomb relative to infinity. So 1 coulomb of joule will have an energy of 300 joule. So if you have, for example, Q, okay, so 3 coulomb, 5 coulomb, it's going to have 300 times 3, let's say, or times Q, joule. Is that clear? So we have potential energy relative to infinity is just QV, because this is the potential energy relative to infinity for 1 coulomb. So if you have 3 coulomb, what's going to be the potential energy? 900 joule. Okay? If you have one electron, the energy will be 300 eV. Okay, we talked about that. 120 volt, each electron will have 120 eV. Okay, because you multiply by the charge. Okay, so definition, the potential energy relative to the ground will be the charge times the voltage. And now, if I bring a charge, I move a charge from potential A to potential B, the difference in potential energy will be Q delta V. Okay? Which is indeed, if you pay attention, you know, because we already talked about that. Yeah. V equals U over Q. Okay, so I don't know where I am. Yeah. Is that clear? So if you have a 9-volt battery, that will mean 9 joule per coulomb. If you have 2 coulomb, you have 18 joule. If you have 3 coulomb, that will be 27 joule. If you have 1 electron, that will be 9 eV. Okay? Okay, so let's do a simple problem. Yeah? Okay, so how do we deal with voltage? You remember problem, which is like in physics too. We always start with the hard stuff, and then here it's gonna get easier because remember the superposition principle. If you want to find the electric field at point A, you need to add the electric field produced by this plus the electric field produced by that. But then you have to be careful with directions, right? And then it could be X component, Y component. But voltage is a scalar. All you have to do is to add. So you don't need to worry about exponents, but it could be positive or negative. So find the potential at A, at point A. Okay, so you use this equation here. You add them up. So by the way, this is a dipole. Okay, I have a dipole here. Okay, so point A. So the voltage at point A will be the voltage because of this charge here, right? So it's going to be KQ1R1 plus the voltage because of Q2. So it's like the electric field, except it's a scalar. So I'm going to call that number 2, and this is number 1. Okay, so it's going to be VA. And then here you have 9 times 10 to the 9 times, this is positive, so 8 times 10 to the negative 9. But this is negative, okay, so you have to be careful not to add. Q2 is negative 8 times 10 to the negative 9, and I forgot the distance. So that will be R1, and this is R2. So this is R1.
0.6 meters.
Here, it's going to be 0.6, right? So this is R1, and this is R2. So what you get? Well, you just add the scalars, right? It's called the principal superposition principle, and you get, yeah. Why is the first one? Why is the first one what? No, I didn't. This just yeah, yeah. It's an equal sign. Only this one is negative, right? So what do you get? 3,000. Okay, so first of all, we can cross this out. So 9 times 8 divided by 0.2, enter minus 9.8 divided by 0.6. 9 times 8 is what, 56? How much is that? What do you get? Why people are staring? Stop staring. Do it. Come on, come on. Yeah, 240. Yes. Huh?
9 times 8 is 72.
No, I found 240. You found something else?
1 times 8 is 72.
Oh my God, thank you. Oh, yeah. I have to go back to my middle school. Yes, thank you. Who said 240? Yes? Someone said 240. But yes, it's 240 volts. Yes? What does it mean? It means that if you place 1 coulomb of charge here, it will be at a potential of 240. Right?
Did we do something wrong? I got 480.
Did you do 72?
72.
No.
I got that from the first one.
First one? Here?
Yeah, I got it. Well, you probably did a double.
Because here it's negative inside. Negative.
Oh yeah, I probably did a double. Yeah.
It's my fault because I put a negative twice. Okay.
Yeah.
Okay, 240. Okay, so if I look at the potential energy, so I have a plus and I have a minus. I'm gonna get something like this, right? The potential here is gonna go up. For this one, it's gonna go down here, boom, and somewhere in between, we have inflection. Okay, so 300, we're gonna be somewhere here, right? It's gonna be here. So it has positive potential energy, which means it's not binding, and of course it wants to go downhill. So it means it wants to go this way because it's a 1 coulomb charge, right? Joule per coulomb. Okay, so this is potential or voltage, and here it will be the x-axis. Is that clear? Oh, can you find that B? B is just in the middle. 0, very good. It's going to be 0. So we are here. Here it's going to be 0. So a dipole, it's a hill, and then it goes down. Right? So this is, here it's a dipole, up, down. So here in the middle, it's going to be 0. Is that clear? Now, question, if I take a... Oh, someone asked me for the book. Here you have the answer. Chapter 23. Unit 23. So how much energy will have a charge of 4 nanocoulomb? So here you place 4 nanocoulomb. How much energy it will have? 4. Exactly. So here at that place, you're going to have an energy of 300 joule for 1 coulomb. So if you have 4 coulombs, right? 4 coulomb, 1 coulomb. So if you have 4 nanocoulomb, right? It's going to be, so 1200 times 4 times 10 to the negative 9. So 1.2 times 10 to the negative 6 joule. No. No, what did I do? Why is there a 4? No, yeah. Is that right?
Yeah. Negative.
Okay. Joule. For if the charge is positive. So if the charge is positive, it has positive energy, so it wants to go down. Is that clear? If you like to have an equation instead, okay, you're going to say potential energy is Q times the voltage. That will be relative to infinity. So potential energy will be the charge, which is 4 times 10 to the negative 9. The voltage is 300. That will be in joules. Likewise, the difference of potential energy between 2 points will be Q, the difference of the voltage. Voltage is already a difference. Is that clear? If the charge is negative, then it will have a negative energy because it's bound, it's very happy. Closer it gets to the plus, happier it gets. Is that clear? So let's see, you have up and then you have down. So let's like typical pop quiz question. A positive charge wants to go up the potential or down the potential? Down. And the negative charge wants to do the opposite. A positive charge will go with the electric field and a negative charge will go against the electric field, right? Isn't that an interesting topic? So if you have, for example, you can make a dipole with 2 Van Graaff generator. You can visualize here the electric field in the vicinity. So this one could be 3000 volts. This one will be minus 3000 volts. And you're going to get something like this, right? Because inside it will be the same potential, inside the same potential. And then you have those electric field lines. This is also, so this kind of stuff you do with your Python, for example. You can do that coding. You can visualize. So if you have water here, imagine this is water, it will go downhill. Is that clear? Oh, by the way, I had someone send me a video. I forgot who. But someone. Now, someone in my other class. Do you remember Faraday cage?
He's building, it builds a tension with it. It's quite a strange.
It's supposed to be in Germany.
You can almost feel the tension. I'm being hit by lightning.
Safe exact? Yes. If he's
My hands are
out,
buzzing.
it won't be.
Hey! Oh, now it's doing stuff to my car. I've got error up on the dashboard. Handbrake light flashing. Adolf just kept piling on the power, but this guinea pig refused to burn.
Okay, so this is a Faraday cage, right? You cannot have an electric field inside, right? You cannot have charges inside, so it will be safe. If it does not discharge the car, touch the car, it won't be fine, right?
Actually, I always wondered why lightning was here.
Oh, but because it's like electricity. It's like it's a plasma. It's called the breakdown of the electric field. If the electric field is larger than 3 million volts, right, per meter, it's gonna break down. So it's gonna, all the electrons will be stripped from their molecules. So you make a pathway for electricity, right? So it's electricity flux. Yes, you're right. When it's coming back, combining, it's gonna emit light, right? So that's your textbook. So chapter 23. And so, for example, the first problem in your textbook, I think it's 23 something. it says 23.4, so it's a solved problem. They have you compute the voltage at point A. Do you see? Minus 900. And then they have you compute the voltage at point B. So it's, I don't know if it's a dipole or not. It's a dipole. And then they have you compute here, right at that point. Question. What's going to be the potential energy if you have a charge of, I don't know, let's say you have a charge of one nanocoulomb. How can you find the potential energy at A? You multiply, right? You already have the voltage, right? So if here the voltage is minus 900 volt, okay, the unit is volt, so volt, okay, the potential energy, okay, of 1 nanocoulomb will just be negative 900 times 10 to the negative 9 joule, okay? So potential energy relative to the ground will be Q times the voltage relative to the ground. Is that clear? Okay, so there is a problem here in your book to do. Okay, so when you have a dipole, okay, so if there is a dipole, for example, the plus and minus, you can do the computation and find the voltage at any point in space. Agree? Right? So you just have to do the math. Now, if it's very, very far away, okay, you see, when you put at the same denominator, so this one will be just r squared. You can do an approximation. R plus here and R minus, that will be those distances. When you massage a little bit, you're going to get that expression here. And what do we find here? What is P? Do you remember what's the physical quantity P? Dipole moment, right? It's a vector. It goes from minus to plus. Because we want to improve in physics and chemistry, they go from plus to minus, right? But we want to go from minus to plus. So that will be the dipole moment. And that will be the voltage at a given point around that dipole at a large distance. So let me ask you something. Remember the electric field of a dipole? It was 1 over distance q. Do you remember? A dipole, it was 1 over the distance q. Okay? And here is 1 over r squared. That makes sense because when you take the derivative of 1 over r squared, you're going to get 1 over r cubed. Right? So electric field voltage. To find the electric field, you take the derivative of the voltage. And to find the voltage, you take the integral of the electric field. So anyway, you can do the computation. There is nothing here to see, just math. So the electric field is the derivative of the voltage. And the voltage is the integral of the electric field. Okay, they are what do you say? Opposite, like integral and derivative. The path. Yeah, remember class? Remember last class we talked about the definition of work. FDS. DS is like a small element, right? A small displacement. By definition of work. Okay, so let's try to see. Okay, before, just like an example of application in medicine, the heart is an electrical system, and the voltage will change with time. But at a given time, we can define a dipole. So, for example, this part of the heart will be at a negative potential, this part of the heart will be at a potential, positive potential, right? You can show the equipotential, and that will be a dipole. So it means here it's going to go down, potential is negative, it's going to be zero at some point, and then it's going to be positive. And if you take an advanced class in, I don't know, cardiology or medicine, you see, they even define a dipole. They're going to define a dipole here. So you can define a dipole here. That will be a vector, P, okay, P, going from this part to that part. And that dipole will change with time. It's easier to describe what's going on in that heart using dipole rather than using charge distribution. Because why do you have a dipole? Here, it's because the charges distribution in the heart will change with time. Right? I think it's sodium. Your sodium goes out, goes in, whatever. So you're going to have more negative charges here, less and more positive charge there. So you can define a dipole, and that's how we can have an EKG, right? And you all know that if it's flat, it's not good. That I know. Otherwise, don't do too much. But you see, you are measuring voltages, right? 1 and 2 and 2. I mean 2 here, 2 there, and 2 there. It's always a property of 2 points. So that physics here has a lot of application. So let's define equipotential. Let's do that together. And then we'll go back to the math. At what time does it open, the pop quiz? 11. Thank you. Okay, so you have 100 volt. Think of altitude. This is 80 volt. This is 40 volt. No, this is 40 volt. And this is 60 volt. So these are equipotential. If I go, so it's a path, right? So I have 1 coulomb of charge in my pocket. I have 1 coulomb of charge in my pocket. And I walk, boom, boom, boom. Am I doing any work? No, very good. Because it's flat. It's an equipotential. I don't have to fight against the electric field. If I go from here to there, is the work done? Yes, it's going to be negative because it's losing energy, right? 100 minus 80 will be 20. Okay, so it's losing 1 coulomb of charge, is losing 20 energy, 20 joule. Is the change of potential will be the same here? Yes, right? Because when you have potential energy involved, it's path independent. Okay, it says that the electric field is conservative. The electric field is going in this direction. Okay, what about from here to there? No work, very good. No work, right? It's a equipotential. You go back to the same place. So if I take my book, notebook, and I go for a walk, right, and I come back to the same place, no work will be done on the notebook. I will be doing work on my muscles, but not on that book. What do you think here? If you have a positive charge, it should look like what? So it's going down. It's like going down a mountain, right? So first it's going to be steep and then it's going to be gentle at the end of the hike. So it should be number 8, right? It's contour lines. You know, when you are doing hiking, the first thing I look is contour lines, right? This is too hard. I'm not going to do that, right? And you have to look because when you go back, when you go one way, it's easier to go up, right? Steeper. When you go down, you want to have a gentle slopes, right? Makes things easier. So you can have, okay, I'm going to save that because it's a little bit harder, but you can have a distribution of charges, right? It can be funky. Okay, we can have fun. I can have a charge here, I don't know, a charge there, a charge there, another charge here, right? And then I can make the equipotential, 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 equipotential. Okay, so it makes something interesting. Contour lines. These are like contour lines, right? But very close to here, you're gonna go downhill. So these are uphill, and then here you go downhill. So somewhere there is gonna be a 0, right? What you see here is that the electric field is always perpendicular to the equipotential. It's showing the way to the positive charge here, which way to go to lose energy the quicker, right? So it's very interesting subject because when you are doing coding, first you do the equipotential because it's a scalar, so it's easier to compute. And then you will do the electric field because you know that the electric field will be the gradient. Gradient meaning the largest slope. So that's how you will do it. So I will come back to this one because your attention span is decreasing. I feel your attention span is decreasing. So I will save it for next time. But here is the idea. This is a dipole. What you see here are the equipotential. At the center here, here it's going to be 0. Okay, the potential will be 0. You have plus and plus. And you can always trace the equipotentials, right? So they are like contour lines. Okay. A little bit of calculus 3 or 4, I'm not sure. So the electric field, okay, the electric field by definition is the derivative of the potential. Right? The electric field is the slope. So imagine, again, imagine you have a, I don't know if it's here over something like this here. What will be the electric field? It will be the slope at a given point, but the largest slope. So water, for example, will always choose the largest slope to go downhill. So the electric field is also the largest slope. Okay, so if you have something like this, that will be the potential here in space. What's going to be the electric field at a given point? Okay, it will show you, okay, the largest slope. Which way to go to lose potential energy as fast as possible. So by definition, the electric field is the slope, right? The largest slope. See, it has a direction. Is that clear? So easy here. You have voltage as a function of distance. So that could be the voltage between two electrodes. Can you give me the slope? So it will be the slope. So rise over run. 2. So what is the electric field? It's going to be the slope. Right? So what is that? That could be, for example, if you have a capacitor plus, 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 minus, 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 minus. You connect your capacitor here to a power supply. Okay, you charge it to a voltage of 20 volt. So this one will have an altitude of 20. So think of altitude 20 volts. So that will be potential energy per unit charge. You can think of that as 0. and the voltage will go down at a constant rate. So the electric field will be, we take the slope, so 20 divided by 10. So 10 here is the distance, so 10 centimeters will be 2 volt per meters. Okay? So what's the electric field? It's the slope. It's showing you how to go downhill the fastest. And the electric field is constant because it's a capacitor. Is that clear? So what's going to be the voltage just here? 10, right? And here it's going to be 5. And here it's going to be 15. It's a slope going downhill. Is that clear? So remember I show you like a simulation. You have 2 electrodes, like a defibrillator. That's what a defibrillator is, right? 100 volt. Okay, so let's try to do this one. Remember, electric field is the slope. A voltage is like contour line, right? It's like altitude. So if you go for a hike, where is it? It's going to be the steepest in this area here or in that area. Yeah, it's going to be the steepest, right? So you know when you decide for the hike, you're going to start here. It will be easier. And then to go down is always the hardest, at least for me. So I will always choose this gentle slope. Otherwise I fall. Okay, so can we find the electric field here? So you find the slope. Rise over run. 10, 10, 10, 10, because it's 40,000. Here it's 40,000 and here it's 30,000. And kind of 10, but 10 what? 10, 10, 40,000 to 30,000. 10,000. Okay, 10,000 volt per meter. You go from 4,000 meter to 30,000 meter over 1 meter. It's a rate, right? So you fall by 10,000 over a distance of 1. So that will be 10,000 meters per meter. Yes, 10,000 volt per meter. Is that clear? Yeah? So here, the electric field will be 10,000 volt per meters. And it's going to be negative, okay? Because it's showing you down slope. So I'm going to put a negative here. The unit is volt per meters, but it's also Newton per coulomb. Because remember, the electric field is a force per coulomb, right? F equals QE in magnitude. So if you have one, I don't know what is mega, well, it cannot be mega, but if you have a coulomb, 1 microcoulomb, the force will be minus 10,000 times 10 to the negative 6 Newton. So that's just a review, right? F equals Q. Yes? Because look, it's pointing to the left, right? Just by looking here. Moving to the left, you go down slope. Okay? Is that clear? But you have to be very careful because, the people building the high tension lines, they have to be careful because charges like to build up on sharp edges, right? You always have more charges when it's very curvy relative one, it's not curvy. So in that case, you're going to have a lot of electric field. I mean, the electric field will be stronger, which means that anything sharp, okay, will have a higher probability to discharge. Okay, you can have a discharge, you can have a spark. So that's why when you walk around those high tension line, you can smell a gas. What's the gas that you can smell? O3, which is ozone, right? When there is a discharge, you're going to make ozone, and it has a very specific smell, right? So this is bad engineering, because if you have too much discharge, it's losing energy, right? So it's losing money. So you want to try very hard not to have too many sharp edges, right? Otherwise you're going to have a discharge. And I can show you that maybe next time, because I feel I'm losing. Can I show you that, or I'm getting tired?
Sure.
Right? I just want to show you something, and then I will open the
Transformer Explorer?
No, oh yeah, I have a nice video to show you. But if you have a Van Graaff generator, let's say, and maybe you have another Van Graaff generator, but with more curve to it, right? Now let's say you have a Van Graaff generator in this shape here, right? So 5,000 volt. So it's a funny, they do have that for demo. They have this. So it's not a Van Graaff generator. Sorry, it's just a conductor that has this funny shape. And let's say I charge it and it's 5,000 volt. Agree? It's just a funny shape, but with some kind of edge. So what's going to happen? The voltage is all over the same. Do you agree with that? So it's going to be 5,000 volt. Like this, something like this, except it's made of metal. Or something like this. Imagine this, okay? This is a good example. Or something that you find on the building here. It's very sharp, right? So you're going to have an electric field, right? So you're going to have the voltage, okay, equals E times R. Do you agree? Because look, the voltage is KQ over R, okay? So that will be the radius here, okay, R. That will be the radius there, right? So here it has a smaller radius, here it has a larger radius, right? E equals KQ over R squared. So do you agree with that? Right? If you multiply E by R, do you all agree that you're going to get the voltage? Okay? Do you see how the electric field is not going to be the same everywhere? Because for the same voltage, if you decrease R, so this is sharp here, what's going to happen to the electric field for the same voltage? If this is going down, what's going to happen to that? If something is constant, so this is constant, if one is going down, the other one has to go up. So the electric field will go up. So here the electric field is going to be very, very strong, where it's sharp. And here the electric field will be less, okay? Because it's less curvy. Is that clear? So that's why you have to be aware of those. That's how the lightning works, right? A lightning will always want to strike where you're going to have that lightning rod. Why? Because here all the charges will build up, okay? And they are ready to receive the lightning. And I have a video for that, just on time, perfect, right? So that was a video of the rocket from Russia, Soyuz. So lightning likes pointy thing. So if you have a lot of lightning outside, you should not stay under a tree. You should not standing up. You can go inside the car, or you can lay flat on the ground. Okay, lighting will go to the pointy things. Why? Because that's where you're gonna have the most accumulation of charges, right? So maybe today I saved your life. Physics save your life, right? So let's go.